Okay, and so today we're going to be talking about applying postulate 6 of the 6 postulates of quantum mechanics in the order that we had given them, which is solving Schrodinger's equation. So the postulate just tells you that you're supposed to solve this equation and doesn't tell you how, so we have to work that out. And there are several different methods depending on the situation, but let me just write down the equation first of all. First of all, it's IH bar, time derivative of our ket that describes the state of the system, and now I'm labeling it by time because it depends on time, is equal to a Hamiltonian times psi of t. Okay, so first let's make a general statement about this, and that is that we can write the solution in the following form. We're going to write psi of t, the thing we're trying to find, as an operator, u of t, acting on what we're going to be given, psi of 0. So somebody gives you the wave function at time t equals 0. That's your initial state. So you're supposed to believe that this is given to you. And then this equation defines the operator u of t, which will be a unitary operator.
Sorry,
So we're going to prove in just a minute that it's a unitary operator. Sorry, was there a question?
I can't see the screen. Is it just me?
Is anybody else not seeing the screen?
I can see the screen.
I can see it.
I can see it.
I'll just log out then. I'll log out and come back.
Okay. Yeah, it seems to be up for me. Okay. So that defines the unitary operator. And so we've translated the problem from finding this wave function that depends on t into finding an operator u of t, which is going to be a unitary operator. We've just changed the problem, but the goal is still the same. Okay, so now let's assume, for now, we'll come back to the opposite assumption later, that the Hamiltonian, whatever it is, has no explicit time dependence. So that would be the case, for example, if it's describing a free particle, if it's describing something in a harmonic oscillator or something like that. But it is a big assumption. Okay, but that's going to make things easier. So now let me give method 1 for solving this. Method 1 is we're just going to guess the answer. So it helps to know the answer in advance when you're going to guess it. And that is that u of t is given by the exponential of minus I h, the Hamiltonian, times t divided by h bar. And that's it. So we're doing a kind of a strange thing here. We're taking the exponential of an operator. And so that's a little bit problematic to define. One way to define what this exponential of an operator is in terms of a power series. So we can define this by its power series expansion. Okay, and just to remind you that for an exponential, e to the anything, let's call it little a, is 1 plus a squared over 2 factorial plus dot 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 plus a to the n over n factorial plus dot dot dot. Right? So the thing that makes this problematic, perhaps, is that we have to assume that this series expansion converges. For real numbers a, this will converge, or even for any complex number, it converges. But operators are a different sort of thing, and so we have to worry about that later, about whether this is actually going to converge. Okay, but for the moment, let's assume it does converge. And now we can do a check. we'll just plug this guess into the differential equation and see if it works. Okay, so on the left-hand side, we had I h bar time derivative, which is I h bar. The only thing that's depending on time here is the exponential. Okay, and then we have psi of 0. And then when we take the time derivative, the nice thing about this is that taking the time derivative is just the same as pulling down a factor of the thing multiplying the time, which is minus I over h bar times the Hamiltonian. So the only reason we can get away with that is because the Hamiltonian commutes with itself. So we can pretend that it's just a number. Okay, and now the I h bar and the minus I over h bar just cancel. This whole thing becomes h times e to the minus I h t over h bar. Okay, and so the whole thing just becomes h times psi of t again, which is what we were supposed to get. Okay, so that shows that this is the correct unitary operator. So notes on this. First of all, let's actually prove that it is unitary. So u of t is unitary. And to do that, what do? We're going to take its Hermitian adjoint, ut of ut dagger. Okay, and now if you imagine expanding this power series and just taking the Hermitian adjoint of each term in the series and then reassembling it, it's clear that all you're going to do is take the minus I to a plus I. You're going to take every h and replace it by h dagger. And then t and h bar are just real numbers, so nothing happens to them. Okay, and now the Hamiltonian is Hermitian because it's an observable. It represents the energy. And so h dagger is the same as h. And so this is exponential of I h t over h bar. Okay, so we've used the fact that h is Hermitian. Okay, and so now we can check that if we take ut dagger, ut, that's equal to the exponential of I h t over h bar times e to the minus I h t over h bar. And now because h commutes with itself, we can just pretend those are real numbers for the purposes of arithmetic. And so this ends up just being the identity operator. We can just multiply everything together as if they were numbers, and therefore e to the I something, e to the minus I, same thing, is 1, or the identity operator. Okay, so that's one comment, is that it really is a unitary operator. Another comment is that the norm of the ket, psi of t, is constant. So that, proving that is a one-liner, let's compute the norm squared of psi of t. And we're going to do it by just plugging in terms of the unitary operator u. Okay, so psi of t bra is psi of 0 u of t dagger. And then psi of t is u of t psi of 0. And now we can use what we just proved, that u is unitary, to make that the identity operator. And so this is psi of 0, psi of 0. Okay, so what does that say? It says if you bothered to make your initial wave function have unit norm, psi of 0, here, then if you follow the procedure for time evolution from Schrodinger's equation, you don't have to worry about it being not normalized to 1 later because it's going to have the same norm at any other time, t. So that's very different from the other way that kets can change in quantum mechanics. In quantum mechanics, there's 2 ways the state ket can change. One is time evolution, which we've just been talking about, and the norm doesn't change. And the other way is when you make a measurement. When you make a measurement, we have postulate 5 that tells us that the state ket changes by collapsing. And there you did have to worry that the norm would change. And so if you're going to use that wave function for something else later, you have to go to the trouble of making sure it really does have unit norm, or make it have unit norm. Okay, so that's good, but now we have to worry about what I mentioned earlier. What if the sum doesn't converge? So what if the infinite sum of e to the minus I ht over h bar doesn't converge? Or maybe in some situations it does, but it's just too hard to actually do the sum, which definitely can happen. Okay, so that means we have method 2, which is going to work better in that situation. So in method 2, we're going to first start with the eigenvalue problem for the Hamiltonian. We're not going to worry about time dependence for just a minute. We're just going to worry about the eigenvalue problem. Okay, so we start with eigenvalue problem for h. And now let's assume that you've actually solved it. And so you've found a bunch of solutions to Hamiltonian acting on eigenkets E rho sub E is equal to the eigenvalue E on the ket E rho sub E. Okay, so again, rho sub E is a degeneracy label for the energy. We'll do an example later where the degeneracy label is coming into play. And we're assuming that these are constant kets, basis kets, so they have no time dependence. Okay, and we're assuming we've found these. Of course, that may be easier said than done, but that's what we're assuming anyway. Okay, so what should we do next? Oh, I know what, completeness, because that's what we always do next. Use completeness. Okay, and so what we're going to do is we're going to say our state ket psi of t at some later time is equal to sum over all energies. And then for every energy, we sum over any degeneracy labels that might happen for that energy. Notice that's why rho sub E has to have the subscript E on it, because one energy label might have a degeneracy and some other energy level might not have a degeneracy. So the degeneracy label depends on what the energy is. Okay, and then we have E rho sub E. We're inserting a complete set of states acting on psi of t. So we've just written one in a clever way. Okay, and then these inner products are a set of numbers, and we're going to call these numbers C, E, rho sub E. And so it depends on the energy, it depends on the degeneracy label, and it also depends on what time it is, rho. Okay, and now we know these kets. And so if we also know these numbers, we will be finished. Okay, so solve for these, and then we will be done. Okay, so to solve for these, we're going to plug into Schrodinger's equation. So we have I h bar time derivative of psi of t equals I h bar sum over energies, sum over degeneracy label for each energy. And now the only time dependence is in the coefficients. So I'm going to write the time derivative as a dot. And by assumption, the basis kets don't depend on energy, or sorry, don't depend on time. They do depend on energy. Okay, so I have no contribution from the time derivative acting on them. That's supposed to equal the Hamiltonian acting on the same state. But that we can write as sum over energy, sum over degeneracy label. Whenever the Hamiltonian acts on an eigenstate of energy, it just gives E. So I can write here E times the coefficient CE rho sub E times the ket E rho sub E. All right. So now what we can do is take the inner product of this equation with an energy eigenstate bra. I'm going to call this E prime rho E prime. Okay, so it's a different energy than we're summing over in the previous expression. And so what we're going to do is we're going to take this part and this part, they're equal to each other, and take the inner product with E prime, the E prime state, and see what happens. Okay, so what we get is both terms have a sum over energy, a sum over degeneracy label, and then the first term is I h bar C E rho sub E time derivative. And the other term, when I move it to the other side of the equation, is minus E C E rho sub E with no dot. And then both of them are multiplied by this inner product, E prime rho sub E prime, E rho sub E. Okay, and so what we did is we took all the constant things outside of the inner product because they're not operators, they're just numbers. Okay, oh, and this is supposed to equal 0. That's what we're getting here. And now, because this is a complete ortho basis, we know what this is. This is a Kronecker delta. It's only non-zero if E and E prime are the same and if the degeneracy labels are the same. And now, since we're summing over all E's and all rho sub E's, the only term that's going to survive is the one term where E and E prime are the same and rho sub E and rho sub E prime are the same. So only one term in the sums survives. And then once we do that, since we only have one term anyway, we can relabel what we were calling E prime as E and relabel what we were calling rho sub E prime as rho sub E, just to avoid lots of primes running around. And so then what we get is that I h bar, time derivative of the coefficient, is equal to E times the coefficient. Okay, so what have we done? We've turned an operator equation into an equation for the coefficients, but actually this is in general, this is going to be an infinite number of different equations. In any case, it's one equation for each E and rho sub E. So this is many uncoupled differential equations. Okay, one for each E and rho sub E. So the nice thing about the fact that they're uncoupled is that means we're going to be able to solve this pretty easily. So to solve this differential equation, we can write it as differential of CE rho sub E divided by CE rho sub E. Okay, now when I divide by it, I'm assuming it's non-zero. But if it is zero, then the solution is easy. Then it's just, the coefficient is just zero for all time. Okay, this equals minus I over h bar times the energy times the differential dt. And now we integrate both sides. Okay, on the left-hand side, we're going to get the logarithm of the coefficient C of E rho sub E. And here I'm going to be careful to note that it's a function of time. And so we're evaluating it at some time. And then on the right-hand side, when I integrate, I get minus I over h bar E times t. Right? Well, not quite right. What am I forgetting?
Integration constant.
Very good. So I should not write period there. I should write an integration constant. I'm going to write an integration constant on each side because they're indefinite integrals. But I'm going to write the integration constant in a clever way. What's going to turn out to be clever later. I'm going to write the integration constant as log C E rho sub E at time t equals 0. In a way, that's just defining what this is at time t equals 0. This is an integration constant. Okay, and now we can exponentiate both sides to get rid of the logarithms. Okay, and we get C of E rho sub E as a function of time is equal to C E rho sub E at time t equals 0 times the exponential involving the energy, e to the minus I E t over h bar. Okay, so we've solved the equation. And now we can plug it in. And so what we get is that psi of t is equal to sum over energies, sum over degeneracy label for each energy, e to the minus I E t over h bar, E rho sub E, E rho sub E, times psi of 0. Okay, this was, this inner product here is the same thing as that. And then the exponential got written here. Okay, so we've solved the equation. Oops, this is the solution. And now if we stare at it, we realize that this part, all of that, must be what we were calling the unitary operator. This must be U of t. So it may not be immediately obvious to you that expression is a unitary operator, but we proved on general grounds that it is. And so this is the solution because psi of 0 acted on by the unitary operator has to equal psi of t. Okay, so just rewriting that, our unitary operator is equal to the double sum. There's a phase factor for each term, which is in general different. And then the rest of it looks like completeness. So in fact, without these phases, this would be the completeness relation. So the phases are very important. Without these phases, would have u of t equals the identity operator by completeness. But in general, of course, it's not the identity operator. That would be also true for t equals 0, because then all the phases are really just 1. But that makes sense. That's saying that at time t equals 0, psi of 0 is psi of 0. Okay, but the fact that this is unitary means that it's a change of basis. And so time evolution in quantum mechanics you can think of as being a change of basis, which is only non-trivial because of these phases. And in particular, the phases are only non-trivial because they're different for different energy states. So only non-trivial because different E's give rise to different phases. If they all had the same energy, then we would just be multiplying everything by the same phase, and multiplying everything by the same phase has no physical effect. So in fact, just to formalize that, that gives rise to the concept of stationary states. Okay, and stationary states are just states that are eigenstates of energy. So suppose that at time t equals 0, my state is an eigenstate of energy. I'm now going to dispense with the possible degeneracy label. I'm just going to, because it actually would play no role in the following. Okay, and so this is some energy eigenvector. It's a specific one though, not one we're summing over this time. Okay, then if we apply what we just learned, the state at some later time is just the same state multiplied by a phase, minus IET over h bar times E. So one thing we've mentioned is that when you multiply by a single phase for the whole state, it has no physical effect. And let's sort of prove that by asking what happens if we measure some observable. And we don't have to be specific about what the observable is. We just say, suppose we measure A at time t. Okay, what's the probability of getting some result? The probability of getting the result alpha we can get from the postulate. It's P of alpha, depending on what time it is sum over alpha, alpha degeneracy label for alpha, psi of t, all squared. Oops, I guess I should sum over rho sub alpha also. Okay, which is sum over alpha and rho sub alpha of alpha rho sub alpha e to the minus I e t over h bar times the energy eigenstate. And now, because e to the minus I et over h bar is just a number, we can pull it out of the inner product and write this as sum over alpha. Wait, what am I doing? I shouldn't be summing over alpha. You should have objected to that. Alpha is some fixed thing. So let me fix this. These sums should have been over rho sub alpha, not alpha. Alpha is fixed, some fixed thing. And for each alpha fixed, we're summing over all the states labeled by rho sub alpha that have that same alpha. Okay. So getting back to this e to the minus I et over h bar is within a complex square. And so I can pull that out and just write it like this. And then there's alpha rho alpha e squared. This complex square of a phase is just 1. And so the whole thing just becomes the probability that you got alpha at time t equals 0. In other words, it doesn't depend on time. So just to formalize that, no matter what your observable was, the probability for any particular alpha stays the same as time goes on. And so that's why it's called the stationary state. That's the reason for the terminology. So in some sense, if you're in a stationary state, nothing really happens. Every observable that you measure, the probability of getting any particular result that you might have gotten just stays the same as time goes forward. And so in that sense, there's no way that you can tell the difference between the state at time t equals 0 and some later time. All right. So all of that was treating the case where the Hamiltonian doesn't depend on time, but now we have to return to the harder question of what if it does depend on time? So what if the Hamiltonian is a function of time? So it depends on time. And just to give an example of where this could occur, suppose I have an atom that's sitting there in some quantum state, minding its own business, and then an electromagnetic wave comes along and hits it. So atom encounters an electromagnetic wave. The atom's composed of charged parts, including the electron. Here's your atom. And then the electromagnetic wave, electric field is coming by. Okay, and so there's some electric field that's changing in time. And so that will give rise, as far as the atom is concerned, that will give rise to a changing Hamiltonian as the electric field changes. So that's just one example that you can think of for when this situation could occur. But then the question we want to ask is, given the state psi of t0, okay, so before I was assuming that it was known at time t equals 0 because it didn't matter. The Hamiltonian didn't depend on time, but here the Hamiltonian depends on time, so I have to be much more specific. I have to tell you at what time exactly t0 am I starting with this state?
Sorry,
Okay?
Professor.
Yes.
I don't want to interrupt. I'm just curious. Could you please go over that example again, briefly?
Which example? The
electromagnetic.
Sorry?
Yeah, the atom encounters an electromagnetic wave. Could you please go over that again?
Right. So the Hamiltonian here is going to depend on the electric field of the electromagnetic wave, and electromagnetic waves have electric fields that depend on time. Right? So as far as the Hamiltonian for the atom goes, the energy that it has is going to depend on what time it is, just because the electric field depends on time.
Thank you.
Okay. All right. So given the state at time t0, the question we're seeking to answer here is, what is it at some other time, some later time psi of t? Okay, that's our big question. And so we're going to answer this incrementally by first saying, to start, what is it at only a little bit later time? So consider only times t that were t0, the starting time, plus an infinitesimal bit, delta t. So in practice, infinitesimal. In practice, what the infinitesimal means is that anything with delta t squared, we get to ignore. Okay? So now we can do what we did before and write psi of t0 plus delta t is equal to, if you solve the differential equation, it's just 1 minus I over h bar delta t h of t0 acting on the ket psi of t0. Okay, so one way to do that is just plug it into the differential equation and see that it works. And here it doesn't matter. I wrote h of t0, but I could have written anything else as long as I'm consistent. It doesn't matter what I wrote here as long as I'm close to h of t0. So it doesn't matter whether h of t0 or h of t0 plus delta t, because the difference is of order delta t squared. Okay, so I made some arbitrary choice of saying, let's use h of t0, but it wouldn't make a difference. But now I'm going to rewrite it in such a way that it actually does make a difference, because I'm going to write this as exponential minus I over h bar delta t h of t0 psi of t0. So that was legal because when I expand out the exponential, just because delta t is infinitesimal, anything with delta t squared or delta t cubed or anything like that doesn't matter anyway. So I haven't cheated there. But the nice thing about writing it as an exponential is that makes it clear that it's a unitary operator. Okay, so this is unitary, which we're going to use in just a minute. Okay. Now, having done that, we've gone from time t0 to t0 plus delta t. Let's advance forward in time by another delta t. So now go to time t0 plus 2 delta t. And we do that by just repeating what we just did. Okay, so psi of t0 plus 2 delta t is equal to, well, what we found before is we just have to multiply by this exponential unitary operator in front. So let's do that again. Okay, we're advancing by delta t, but now we have to be a little bit careful because now it's h of t0 plus delta t, since we're starting at t0 plus delta t and going to t0 plus 2 delta t. Okay, so I have that, and then I have the state that I had before. Minus I over h bar delta t, h of t0. All acting on the initial ket psi of t0. Okay, now before continuing, let me just mention that it might be tempting to combine these two exponentials, but you can't. So that exponential and that exponential cannot be combined. And the reason is because we're assuming the Hamiltonian depends on time, and therefore they don't commute. They're not just like numbers. So can't combine because the Hamiltonian at one time, t1, commuted with the Hamiltonian at some other time, t2, is not zero in general. Okay, and these are at different times, t0 here and t0 plus delta t there. Okay, so anyway, let's continue doing this. We can just keep adding delta t's, and what will we get in the end? So now go to t0 plus n delta t, and then we're going to find the state at that time, plus n delta t here, is going to be a big product of exponentials. So we're going to take the product from n equals 0 to capital N minus 1 of a bunch of exponentials, which look like this: e to the minus I h bar delta t, the Hamiltonian of t0 plus little n delta t, all acting on our initial state ket psi of t0. And when I write this big product of exponentials, it's understood that the order matters. And in fact, smaller n's have to be on the right, smaller little n's. Okay, and that's because of this statement made again in the little n equals 2 case that, or the big N equals 2 case, that you have the order matters. Okay, so now if you've done that, now you can take the limit of a very large number of these operations. So now we're going to take capital N times delta t to be t minus t0, the total elapsed time, with delta t goes to 0, and therefore capital N going to infinity, but with their product held fixed as t minus t0. Okay, so let's write what that equals. That means psi at the time t is equal to the limit as n goes to infinity of a bunch of products, n equals 0 to capital N minus 1, of a bunch of exponentials, each one involving a Hamiltonian at a different time, unfortunately. And so all of that mess is acting on the initial state ket, psi of t0. Okay, so this part right here is a product of unitary operators, and so it's unitary. So by the way, that was why, if we go back a few steps, that was why here I bothered to change this into an exponential, even though in the delta t infinitesimal case, they're the same thing. Just writing it as a unitary operator and then carrying it through, now we have a product of unitary operators, and it's manifestly unitary. It would have been the same if I'd left it as 1 minus IH bar blah, 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 but it wouldn't have been so obvious that it was a unitary operator. And here it's sort of built in. Okay, so that's true. And then another thing that's true is that, let me use a different color for this, just to do that. If I take the whole thing, including the limit, that is a unitary operator, which depends on time and depends on what starting time was, right? It's got both t and t0 built into it. And this is sometimes known as the evolution operator, the unitary evolution operator. Some books call it the propagator. I can never call it the propagator because I work in high energy physics where we use the word propagator for something else. But in any case, it's a unitary operator that depends on the starting time and the ending time. So there's another way of writing this unitary operator. This is really the same thing. It's just a matter of notation. But one writes a capital T symbol that I'll come back to in a minute, times an exponential, in which now I take this infinite product and turn it into an integral. So it's minus I over h bar, integral from t0 to t, dt prime of h of t prime. Okay, and now getting back to what this t thing is, this is known as the time ordering symbol. Okay, and all it is it's an instruction in whatever follows, namely this exponential of an integral, to put every Hamiltonian in the right time order. So put each h of, let's say, t1 to the right of h of t2 whenever t1 is less than t2. Okay, so that's important because when we wrote the product, we had that rule, and we can't change the rule now because the Hamiltonians at different time don't necessarily commute. Okay, so that's what the time ordering symbol means. This exponential of an integral of h's involves, in general, lots and lots of h's. And so you have to, whenever you see any two h's, you have to put them in the right time order. Okay, so now some properties of this unitary time evolution operator include, first of all, that let's say I start at t1 and I go to t2, and then I go from t2 to t3. So I can write that as u t3 t2 acting on the operator t2 t1. Okay, so we start on the right. We go from t1 to t2, then we go from t2 to t3. That's the same thing as going directly from t1 to t3, which I write like that. Okay, another thing is that it is indeed unitary, but there's one more thing we can say about it when we talk about its unitarity, and that is that if I take u of t2 t1 and I take its dagger, its Hermitian conjugate, that's the same thing as the inverse. Okay, that's saying it's unitary, but now there's a bonus which says this is also equal to u of t1 t2. Okay, and so what is that? What is the physical interpretation of that? That's saying if we evolve from t2 here to t1, that's the same thing as the inverse of evolving from t1 to t2 here, which is just what you'd expect. Going forward in time is the inverse of going backwards in time. Okay, so let me just mention one more thing, which is that you can assemble all of this into a different way of writing, which is called the Dyson series. So you can show that the unitary operator u of t t0 is equal to the identity plus an infinite sum, n equals 1 to infinity, minus I h bar to the nth power. And now we're going to write out each integral. So there's an integral over t1, and then there's nested within it another integral from t0 to t1 of dt2. And you keep going until you get n of these integrals. And then you have all the Hamiltonians, h of t1, h of t2, up to h of tn. Okay, and so these, they don't commute, and so the order matters. And then the other thing that's interesting about this is that because it's a bunch of nested integrals, there's some combinatoric factor which turns out exactly cancels the fact that there was a 1 over n factorial usually in the exponential, but here there isn't. So note, no 1 over n factorial factor. That's not a typo, that's really supposed to be that way. So that's the Dyson series representation of the unitary operator that works in the case where Hamiltonians don't commute at different times. And where this is usually applied is in perturbation theory, which we're not going to talk about this semester, but you should know that it exists. So in perturbation theory, what you do is you treat the whole Hamiltonian as a simple part with no time dependence. Plus a more complicated part that's got the time dependence in it, which I'm calling h1 of t here, where the complicated part you hope is small, or you can treat it as small, even if it's not small. Okay, and because it's small, you keep only 1 or 2 of these. Okay, and so by doing that, then you can simplify things. You don't have to keep track actually of all of these terms here. There's only a few terms that you have to keep track of, and then you assume or hope that the rest are small. Okay, so that's time-dependent perturbation theory. There's also time-independent perturbation theory, which if you take physics 661, we will treat before we get to this. So that's a long way in the future, but it's good to sort of see now where we're going. All right, so sorry I went a little bit over time, but I will now stop the recording.